Hello, Chemistry 125 and 128 students. This is a problem on the freezing point of a battery solvent, specifically looking at freezing point depression. Alright, so what's the background? Redox flow batteries are the most probable technology to integrate more wind and solar energy into the power grid. Commercially available redox flow batteries are based on aqueous chemistries, and many scientists worry that the batteries will fail in cold climates or the water-based electrolyte would freeze. To address this problem, electrochemists are working to develop redox flow batteries that use organic solvents with lower freezing points. One such electrolyte is based on using propylene carbonate as the solvent and tetrabutylammonium hexafluorophosphate as the salt. Given that a prototype battery used an electrolyte with a 0.85 molar salt concentration with a density of 1.21 grams per milliliter, what is the freezing point of the battery solvent? If the experimentally measured freezing point was negative 56.3 degrees Celsius, what is the real value of the Van Hoff factor? So this question has two parts. All right. So I cut the text down just so we can focus on what's important. And in this problem, what we're looking for is our freezing point depression. And so we have an equation that's very similar to our boiling point elevation equation, where we have our change in freezing point being equal to our Van Hoff factor, I, times our freezing point depression factor, Kf, times the molality of the solution. So we were given I, this is 2, and we were also given the freezing point depression factor, that's 4.34 degrees Celsius per molal. So we need to figure out what the concentration of salt is in our solution. Okay, so to do this, we're going to make this assumption that we have a liter of our solution, and we know the density of the solution, so from that we can figure out the mass of the solution. So we need to go from liters to milliliters, since our density is in grams per milliliter, and we see that we'd have a total of 1,210 grams of solution. All right, we want to get the mass of the solvent, so we need to figure out what the mass of our solute would be. Since we know that the concentration in molarity is 0.85 moles per liter, we can simply use the molar mass of our tetrabutylammonium hexafluorophosphate to figure out the number of moles of solute in that liter. Sorry, the number of grams. And through multiplication, we would see that we have 329.32 grams of solute. So a big chunk of our solution is actually the solute. All right. So now, since we know the mass of the solvent is equal to the mass of the solution minus that of the solute, we can calculate that we have 880.63 grams of solvent. In this case, the solvent is propylene carbonate. So now that we know the number of moles of our salt and the mass of our solvent, we can convert that into kilograms because that will give us molality. The moles divided by the kilograms gives us molality. We can calculate that the molality of our solution is 0.965 molal. So plugging all of our known values in, we can determine the change in our freezing point, or freezing point depression, and this is 8.5 degrees Celsius. So we get a pretty good drop in freezing point to bring us to negative 57.2 degrees Celsius. All right, so that was the first part of our problem, and let's look at this next part. So if we want to figure out the Van Hoff factor based upon an experimentally measured value, we can rearrange our freezing point depression equation so that we're solving for I, the Van Hoff factor. We actually have all the information that we need. To get our change in freezing point, we take the actual freezing point minus the new freezing point. This is 56.3, and we divide that by our freezing point depression factor and the concentration of our electrolyte in molal. If we do that, we'd see that our value of I, or Van't Hoff factor, is 1.79. So it is a little smaller than the ideal one, which is 2.